related rates. So when we talk about related rates, we're going to look at a lot of derivatives and put them all together. But before we do that, we're just going to look at something simple. And just want you to consider 3 over 4 times 4 over 7. Now, one way to look at this is that you could recognize that the 4 and the 4 would cancel out, and we just end up with 3 over 7. And we're actually going to use something very similar, but in calculus. So if we were after an expression for dy dx, we could consider an expression for dy over something times something over dx. And if those two things were the same, they could be anything. They could be derivative of z, because if they were the same, they would cancel out, and we get an expression for dy dx. And this is essentially just a chain rule, and we're just going to use it with some real world examples. So we have a spherical balloon being inflated so that its radius increases at a constant rate of 3 centimeters per minute. So its radius is increasing at 3 centimeters per minute. At what rate is its volume increasing? So we want to know, how is the volume increasing? So how is the volume increasing when the radius of the balloon is 5 centimeters? Now, let's just go back over and check what we said here. So when its radius is increasing at a constant rate of 3 centimeters per minute, so we actually want to write, if we're speaking about a rate, we can write that in terms of derivatives. So we could say that dr dt equals 3 for this. So this is the rate in which the radius is increasing with time, equals 3 centimeters per minute. And over here, we were talking about, we want to find the rate in which the volume is increasing. So we want to find dv dt. This is what we want to find. We want to find the rate in which the volume is increasing. So if we're after dv dt, and we know an expression for dr dt, what derivative do we need to multiply to get the required derivative? Well, we need a dv on the top, and this has to be the same as the numerator in the other one, so that's dr. So we need an expression for dv dr. So how can we relate the volume and the radius? Well, we know it's a spherical balloon, so we should be easily be able to come up with an expression that relates the volume and the radius. So we know that the volume of a sphere is 4/3 pi r cubed. And now we can easily find an expression for dv dr, because all we have to do is differentiate. So we can find dv dr. So we bring the 3 to the front, it'll cancel with that 3 in the denominator, so we're just left with 4 pi r squared, we minus 1 from the power. And it was after the rate of the change of the volume when r was specifically equal to 5. So we can go ahead and sub 5 in for r. So we're just going to get 4 pi times 5 squared. 5 squared is 25, and 25 times 4 is 100. So we're just going to get 100 pi for dv dr. And now we have everything we need to find dv dt. So we know dr dt is equal to 3. And now we know dv dr equals 100 pi. So we know dv dt just equals 300 pi. And if we wanted to include units, we can say that units are in centimeters cubed per minute. And we know that because our measurements are in centimeters, so our volume had to be in centimeters cubed, and we knew our time period was minutes, so we know it's per minute.